Okay, so let's dive in then. Let's dive in straight to uh, today's. A lot of people have still not joined yet, but then time is going, and so we'll start. So yes, again, good afternoon. Welcome to those of you who have just joined. Today is going to be a practical hands-on session, and we're going to be looking at some of the things we've covered the last few sessions. All right, so without wasting much time, I would quickly dive in and then we start. And so today we're going to be working with a crime data that we've been playing with for some time now. And we'll also go ahead to look at some time series data, like I promised you the last time. So we'll look at some time series data that I sorry, that I extracted from some satellite data. And this is data that I use for my PhD research. I just pulled it off some of my old folders that was sitting somewhere on my hard drive. So we're going to look at one time series. We're going to look at how you can analyze the time series, look at the trend, look at the seasonalities, try and see how we can also, if time permits us, look at how we can apply some smoothing functions and also some interpolation functions just to fill in the gaps, and then see if we can reduce the noise in the data a bit by applying some smoothing functions. All right, so without wasting much time, let's dive into today's. So, like I said, today we'll be working on the crime data. We'll explore it, then we'll look at some statistical tools concerning that. So, I have what I have done since we explored the crime data the last time was to save it in a much more clean format, so we don't have to we don't have to go and add all those headers again and all those things. I've saved it nicely. And so what I'll do is I'll just read it into a variable called crime df. By the way, if you think the font is too small and you can't see, just let me know so that I increase it a bit. Okay, is it okay, or should I increase it a bit? Let me see if I can increase that a bit. I think it should be fine now. Let me just hide the sidebar. Okay, the File Explorer. Okay, so we're going to read in. So first of all, we need to restart our kernel, and we need to read in all the modules that we'll be using. So far we'll be using pandas, and then we'll also use NumPy. So read that in, and so we're going to look at data. So we're going to read that data in. So read CSV, and then the data I already have it in the same folder where I'm writing or where I have this Jupyter notebook running. And so the data is called crime. I think it's crime data clean. Yes, crime data clean CSV. So this is the data. So I'm going to run this, and then if I come here and I just want to see the data that I have read, I'll just have to do crime df.head, and that should show me that the first 5 lines, just to show me that yes, I've correctly read the data into the Jupyter notebook, and this is the data, and it's not too different from what we've been playing with. It's just that this is like a cleaner version of it because I have taken care of some of the missing data. I have added all the headers, as you can see, so you don't have to. I don't have to run through all those things again because we had already covered some of those things in the previous section. So the next thing we'll be looking at is I think we won't be working with every single column over here. So to make things easier for us, we're just going to bring in some. Just give me. Let me just. No, let me just come here and then come and copy the some of the columns that we'll be using. So remember, I just copied this from an old script where I listed some. Um, sorry, sorry about that. So I've just put some of the headings into sections and I've put them in a list. And so we can just, if we wanted to look at just the columns that pertain to age, we'll just call the age list and then use that to slice our data to just show the age columns. If we wanted to look at crimes, sorry, income levels. We can look at that as well. Let me just rename this to income, and then there's also the crime one here, the various types of crime that are in the data. So let's run that. And so the first thing we'll be looking at today is data sampling, which was one of the very last things we covered the last time, right? And so, but before we do that, let's quickly do data sampling. So data sampling, we talked about the fact that it has to do with you have your population and you're trying to just sample some few data points from the population and then try and see how you can then analyze that one if in case maybe you think the data points are too much for you to use, or you also think or you also have a situation where your PC is not or your system is not able to read in all the data points into memory and run, then the best thing would be to sample some data out and then use that. So let's look at how we can run some data sampling. But before we do that, I'll just run my crime data again and just look at the statistics. So let's do data crime underscore df and let's describe that. Let's describe it to look at some summary statistics. So these are the summary statistics. We have 2,215 data points. And for all the columns, we have the minimum, min, max, we have the average, we have the standard deviation, and then we also have the interquartile ranges. So we have the lower 25, upper 25, and then the median, which is the 50%. But with the population, the data is not showing very well. So what I'll do is I'll just round this up to 2 decimal places. So I'll just call the method round on the whole. So whenever you do a describe, it still creates a data frame, and you can just call the round method on it and say you want to round it up to 2 decimal places. So when I run this, it should then show this neatly with every data having just 2 decimal places after it. So just 2 values after it, which looks a bit cleaner now. Okay, so we've looked at the entire population. So I'm assuming that this 2,215 is the population, and I want to sample about half of that, just 50% of that, and use for my analysis. So let's look at something and let's see if the sampling method here works as expected. So what we are going to be looking at is we're going to take the crime data and then but first of all let's store this. We are going to sample about 50% of the crime data. So let's store that into another variable called subsamp, for instance. So that's the variable, and so we are just calling the crime underscore df, and then we say sample. So when you call the sample method on the data frame, then you can say, so usually this one does a randomized sampling, which was one of the examples we looked at. And if you look at some of the arguments that go in there, if you maybe you have a specific number of samples that you want to extract from the population, what you can do is use the n argument over here. So with the n, you just enter an integer, which is a number. So maybe I want to sample 5, I want to sample 10, I want to sample 50. You go in the sample at random 50 data points at random from the population, and then store that into the subsample. But if you're not interested in a specific number, but then you're rather interested in a percentage, but you're rather interested in just sampling just a percentage of the data or a fraction of the data and not everything, then you use the frac argument. We can ignore the other arguments for now, but then this one, n, the number of items from the axis you want to return, it cannot be used with frac. So if you're using the fraction, then you can use the number, but then you can use them interchangeably. You can use the two of them together. You always have to choose one and use other. So what we are going to do, we just look at an example. So let's say I want to sample 50 data points from, or 50 records, sorry, the 10 years records. We want to sample 50 records from the crime DF. We can just call the n argument and then pass the number 50 to it. And if we run that, it should, then if we run that and sorry about this. If we run that and we look at our subsump, we should have, and we just look at the shape of this, we should have 50 records of the 39 columns just sampled at random from the entire data set, right? And if we want to see if this 50 is representative of the entire data set, what we can do is to call the describe method again, just to look at the means of this and see if it's a good representation. So if you can take the population column, or you can even take the household column. And I am not presenting a PowerPoint slide. I am showing coding. So the one saying they cannot see PPT, I'm sorry, but I am not. No, I am not. I'm not making a presentation. I am showing the Jupyter notebook, and that is what we are using today. So is that what you cannot see? Please clarify. Is it the Jupyter notebook that you cannot see? Please unmute your mic and let me see what the problem is. And let me know what the problem is. Is it a Jupyter notebook you cannot see, or you cannot see my screen at all? Because I am not showing a PowerPoint slide.
Jupyter notebook.
All right. Let me stop.
It is okay. It's okay.
Let me stop sharing my screen and share again. Okay, hopefully you can see now. So to see if the
No, sir. I
sorry.
can't. I don't see.
Okay, you.
I can see your screen, so Leo has to check his.
Yeah, you have to check your device, okay, from your end, because probably there's something wrong with from your side. So first of all, can you see me? If you can see me, and if you can see me, then you can see that next to me will be the screen that I'm sharing. And if you click on that, and if you click on that, you can actually double click on that to make it your current view, and then you can see the screen. Okay. All right. So I'm going to continue.
It's okay, doctor. It's okay.
Okay. All right. Okay. So like I was saying, we are looking at data sampling. So we were looking at the population. We're just trying to sample some few data points from the population, and to see or to test if the sample that we've selected from the entire population is a good representation of the population. What we are trying to look at is to just calculate or try to look at the summary statistics together, comparing both of them. So this is a sample of just 50 data points. And as you can see, the count here is 50. And the count here is 2,215. And this is the summary statistics for the entire data set. And I've gone ahead to run this sample function over and told it to sample only 50 data points, and it sampled it. And from the 50 data points, if our 50 is a good representation of the population, then if we take a column like the household, for instance, and you look at the average, here we are looking at the average of the 50, the average of the household size for the 50 data points is 2.6. And the average of the household size for the entire 2,215 data is 2.71, which is not too far from what we are seeing from the sample data sets, or from the randomly sampled data set. So we can draw some conclusion on based on this that, and if you look at the standard deviation to is 0.33, and you're seeing a similar thing over here, 0.33, and then if we look at the median, for instance, which is the 50% quartile, is 2.59, and the median over here is 2.6, which is not too different from, and you can see that for the other races as well. So race percentage black, the mean is 9.3, the mean over here is 10. So we can see that we've just sampled some out of the data, and because the sampling has been done very well by the sampling method that we used, then you could see that the sample is somewhat representative of what the population is. So we can go ahead and start running our statistical test on this sample. And instead of running the statistical test or exploring the entire 2,200 something data set, we are just sampling a few to use. So, but then we are not going to use 50. I think 50 is just too small to represent data that is 2,000. So let's take just about, let's take a fraction of that.
No, what I don't say.
Let's take a fraction of that. And so what we're going to do is that we're going to take just about 40 to 50% of the entire data. So instead of using the number, we're going to use the frac option, and then we say we want to take only 50% of the entire data set. And then when we run that, so it's trying to then go in there and then sample just about half of the entire data set. What's happening? Sorry. Whenever you use the fraction, it's supposed to be decimals and not the actual. So I'm supposed to do 0.5, not the. Okay. So 0.5 here, if you multiply by 100, you're going to get 50%. And so we are taking 0.5 or 50% of the entire data set. And when we run the describe again and we round it up, to 2 decimal places, then what we are getting is these values over here, and this is 1,180 or 108 data points. Okay, I think this is still a lot, but it's okay. We can work with this. So over here we are looking at a sample, and when you look at the samples, if you just take household, or let's even look at population. The population, the mean over here is 53117, and the mean over here is 54121. So it's still 53. It's about, the difference is about 1,000 difference, but then it's not too far from, I mean, if you're looking at the huge numbers here, and if you look at the standard deviation here, standard deviation is about, it's about 200,000, and we are looking at the same, nothing too different from the population. And if you look at the other columns too, we are getting similar values across board for everything. And so we can then conclude that our sampling that we've done, our randomized sampling that we've done from the population, is a good representation of the whole population. So what we can look at from here onwards is just to look at some distributions. So we can look at some distributions. And so the first thing we're going to look at is try and see if we can plot a box plot. And for those of you who still not understanding the entire concept of the box plot, I brought this here again just to guide you so you understand exactly what it means. So when we take a box plot, what we are trying to look at is, we're just trying to look at the same thing that you are seeing over here, this describe that we've done. And whenever we call the describe method, it calculates the mean, it calculates standard deviation, it calculates the minimum, maximum, 25th percentile, 75th, and then also the median, which is the 50% percentile. Okay, we're just trying to look at that same thing, but what we don't get to see here is we don't get to see the outliers and all those other things. And so to have a pictorial representation of whatever we are seeing here, the statistics that has been extracted over here, we're going to use what we call the box plot. And the box plot is going to show you something that looks like this, but then maybe it might orientate it and make it from top to bottom instead of us seeing it from left to right. And when you see this box plot, all it's telling you is that values that fall within this range are the interquartile range. So we are seeing the The Q1 over here is the 25th percentile, which would be the same as we are seeing over here. The values that fall at the top end of this will be the Q3, which is the 75th percentile, which is the same as what we are seeing over here. And then the yellow line that they show in the box plot when you plot it will be the median, and which will be the same as the 50th percentile. Okay, and then it would also show you the minimum and then the maximum. Minimum and maximum within the interquartile range. Okay, it will show you the minimum and maximum within the interquartile range. The reason why it tries to give you the minimum and maximum within the interquartile range is that we are trying to also determine which of the values are outliers, which of the values are lying or do not occur frequently but are in there. And so those values then become your outliers, because frequently when you try to calculate your interquartile ranges, those values don't appear frequently. And so what the algorithm tries to do is then to just say, okay, those numbers that do not appear very frequently in the entire data set, we'll label those ones as outliers because they appear only one off and not all the time. Okay, so let's try and do some box plot on the sample data set just to look at how it will look like. So no, let's see if I can. Yeah, good. Okay, so and to do the box plot, we are going to be using the last time we were using SNS, but then I'll also need, so let me see. So I'll say import, we'll use matplotlib and then SNS. Matplotlib, we'll use a package in there called pyplot, and then give it an alias or give it a name, which is PLT, which is the standard name that everyone uses across board. So PLT will be the alias for this whole matplotlib.pyplot, so that subsequently when we are writing the code, you don't have to be typing this long thing again. All you need to do is do PLT and it to represent this thing. And then we're also going to bring cborn, and then we are going to call it SNS for short. Okay. So while we wait for that to load, what we want to do is to do a box plot. And so because I want my box plot to look a bit nicer, I'll do a PLT and put the whole box plot in a figure. In a figure that I can control the size. I'll give it a fixed size of about let's say 16 by 5. Let's make it by 6. So that'll be the size, and then I can do an SNS dot box plot. But I don't want to just plot everything. I'll just try and look at just some few columns, because if I try to bring everything, it might be too much. And so we'll look at the data, we'll pass the data in there. We'll pass the data in there, and then we're going to say our data is equal to sub sump, but we are looking for just some few columns in there. So we're going to do a look, and the look, we want every column. Sorry, we want every record, but then we are looking for just columns that fall within the age. Yeah, let's just look at the age, and so we'll look at just the age, the list that is in this age. So we'll say age, and then when we run this, it should give us a nice box plot. Okay, so it gives us a nice box plot, and this box plot is telling us that, well, if you look at all the age columns, this is how the data is distributed. Okay, and the age column, if we go back to try and understand what it is, it's not actually the actual age, but it's looking at the percentage of people that fall within 12 and 21, percentage of people that fall within 12 and 29, percentage of people that fall within 16 and 24, percentage of people who are 65 and up. Okay, so these are percentage values and not the actual ages. And so what is that telling us? If we take the 12 to 21, then you're seeing that your interquartile range is between percentage-wise is between about, let's say, 12 to about 17 or 18% of the people fall within the interquartile range, and then the median percentage age is, let's say, about 13 or 14, because I don't know I don't have that. I'm just guessing because of this value range is about 5 points over here between. So I'm just guessing what this lies on. And then the maximum is about 20%, minimum is about 8 or 9. And then there are a lot of outliers. And so there are some few communities where, even though the percentage age range falls within this, there are few outliers that fall outside that. So there are few communities where in that data set, because the data set is community based, and so there are few communities where the number of people that fall within this age range are very high, and so you can see those outliers here, and then you can see that there are some communities too where the people who fall within this age range, the percentage of people who fall within this age range are very low. And so you can see that there are some communities, they are very young people, and there are some communities that have the age of young people are very low, and you can see that across. But so you can see that across board for all of them. And so based on what we've learned about the box plot, you should be able to then, deduce or explain some of this changes or different shapes of the box plot that you're seeing. But then one thing I also taught you was the fact that instead of using the box plot, you can also visualize this by using just a histogram. So we also looked at the histogram and we tried to explain what the histogram was, right? But even before we move forward, one thing I want to do is let's compare this to the population. Okay, so I use the subsample over here, but let's run this again for the entire population and see if the data that we've sampled is representative of the entire population. And so this is something we can use. So instead of using the subsample, I'll just use the crime DF, which is the entire data set, and then plot the same thing and see how different that looks from. So this is the sample, the 50% that we sampled at random, and then this is the entire population, and we are not seeing any much difference in there, right? You can see that the distributions are still the same across. So if you look at this minimum maximum is around for 12 to 21. It's between, let's say 9 and 20. Let's come here and look at the same thing. Yeah, we are seeing a similar thing over here if you look at where the things fall. And so once again, we've been able to prove that the data that we sampled from the population is not too different from what the entire population is. And so then we are confident that if we go ahead to run analysis on the subsample, we can make inference about the population. So if we say that, okay, based on the sample, the age range in a particular community lies between, the percentage age within a particular community lies between 8 and 20, or 8% and 20, then we can make that inference about the population as well, because we are seeing that the sample data is a good representation of the population. But another thing we tried to look at was the histogram. So let's try and plot histogram. I'm just trying to draw your attention to certain things over here. So let's look at I think what I'll do is I'll rather send this up here and then bring the subsample down here. And so I'll rather plot the population up here and then come and bring the sample DF, because I want us to plot the histogram and then also compare the histogram to the box plot to see if the histogram is telling us anything different, because the histogram also tells us but then with all this plot, it's a matter of choice and you being able to get which of the visualization techniques gives you the best view, so you can explain to whoever it is that needs explanation or whoever you explain the data to. So you can decide to solely go with box plot if that is what you think would make sense to your clients or your bosses or whoever it is you're going to run your analysis for. Or you can decide to use a distribution, or you can try to use a histogram if that is what you think your bosses will understand better. So let's just do the same thing, but then with a histogram. Okay, but in this case, let's just look at one. So let's just look at one of them. So this day we'll look at the age percentage between 12 and 29. Okay, but then for histogram, so we'll do for histogram, what's the best? So we'll still use SNS, and then we'll do a histogram plot. The data that we are going to use once again is the subsample, but then we are sampling just the age out of it. And so we look at age. If I run this, it's going to try and plot something like this it's going to try and plot something like this for all the different columns in there. So you have a distribution, it's plotted a distribution and it's giving them colors for all of them. But then this is difficult to see. There's someone wanting to get in the room. Let me let them in. Okay, but that's difficult to. So I mean, you can see some of them clear, like for the age between 12 and 29 percentage age. This is the histogram for it, and then it's put all the histograms in one plot and it's colored them nicely. But then it's difficult to see because some of the histograms are behind others, and so you can't see clearly. So what we then want to do here is we want to say, okay, we just want to see one, so we can say our x. What it should plot on our x-axis of this plot should be just the age. Sorry, it has to be a string. Age PCT 12 to 29. So let's just run that just to get one histogram out. And you can see this is just one histogram for the percentage age that falls between 12 and 29. And from here, you can also see how it's distributed. So you can see that, okay, the number of people that fall within the 10% range of this are here. And the majority of them fall between, I'll start from 20 all the way to about 31 or 32, right? And then we have some few people falling between 30 and 40. And then we have some outliers here all the way to 70. Now let's see if a similar thing can be seen in the box plot as well. So just bear this in mind, and then we go to the box plot, and then we are seeing this is the box plot for that particular plot again, right? So once again, we are seeing that a lot of the interquartile range, a lot of the data points fall between, let's say, 19 to about 31, 32. So let's see over here as well. We are seeing that over here. So this is, if you map this from here, we're talking between 18, 19, and then all the way to about 32, 33, thereabout, or 35. Let's say 35. If I had a ruler, maybe I'll just put the ruler here and draw the line so that I can see exactly where it is. And then after that 35, you see that there are a lot of outliers that go all the way to 70. And you can see that here as well. You can see a lot of outliers that are going all the way to 70 over here as well. And so this one is just giving us another representation of the same distribution, but then from a different point of view. The way I like to see this is that the box plot is looking at, so if maybe you were standing up here and you were looking down at the histogram, what you see is something that looks like a box plot. So if you're standing up and you look down, you'd see something like this. But then if you're standing either to the left or to the right of this box plot and you're looking from this angle, then you're going to see something like this, right? That is how I like to think about it. I mean, you can also have your own perception or whatever, but then that is, for me, that is what makes sense. And so there's also a distribution plot. This tells you that, okay, but then with this one, what it tells you is the additional information you get over here is that it also gives you counts. And so here then we are seeing that, okay, the number of people who fall within the percentage age of between 20 and 30 are ranging between, let's say, 50 So that means arranging between, so the number of data points in the records, right? Or the number of records that fall between 20 and maybe 30 are starting from here. So if we say the 20 start from here, then we are saying that, okay, start from maybe it occurs 25 times all the way to about 120 or 125 times or something, because we are seeing some peak over here, right? So if you're looking at this, the value that fall within this range, this is the number of times they are occurring. So we are seeing some form of a frequency count as well, in addition to the way it's distributed. And that is what you don't get from here. Here, what you are seeing here are the actual percentages, which in this case we are seeing on the x-axis over here. Okay. And then in addition to the percentages of the values itself, we're also seeing a count as well. That is what the histogram gives us. All right. We can also look at the same histogram again for maybe another column. Let's look at that for the, let's look at it for the 65 app and see if, so let me see, it's BCT 65 app. So look at 65 app. Yeah, so this is the 65 app. We are seeing there are some few outliers which are very close to 50. If we go up here, we are seeing the same, I think it's just one outlier actually, that is almost close to 50 as well. So we are seeing that a lot of the data lies within this range from about 22 to about 5. If my eye says me either 5 or 4, and then if we come here, we are seeing that, okay, it's not even 5, but then it's closer to the 10. So let's say 9, and the upper limit is around, we're seeing the upper limit here to be, looking at this, right? Sorry, I was looking at the wrong one. We're looking at this one, yeah. Sorry, so we're looking at the wrong plot. So this is the 65 upwards. So yeah, so like I was saying, it's not 5, but then it's even lower. When it's 0 and there are 5 points between here and here, then we're talking about maybe 2 or 3. And then this, let's say majority of it ends around 20, 21 thereabout, before we have some few outliers here. And that is all. And we are not seeing any outliers that go beyond this point. All the outliers are high ones. And so there's a different way of representing it. And over here too, we are getting the count. So that is data distribution. So we've looked at some form of distribution. The next thing I want us to look at is to also look at some of the statistical tests. So we'll start diving into statistical tests. But then before I go into that, are there any questions? Are there any questions for me? Is there anything that you're not clear about? Okay. So if there are no questions, then let's move to the statistical test that we're looking at. So we've looked at sampling today. We've looked at we've looked at some visualization. So for those of you who just joined, I just allowed a lot of people in right now. And so what we've been looking at so far is we've read in some data. We tried to do some data sampling that is trying to get some fraction of the data out of the entire population. And what we did was to then run some sample. So we sampled about 50% of the entire data, 50%, which was about 1,001. And we compared the means of the entire population. For instance, if we take the mean of the population of the crime data for the household size, 2.1, and then we look at the sample data to 2.71, sorry, and we look at the 50% that we sampled to the mean is the same. So we concluded that the mean was a good representation of, sorry, the sample data was a good representation of the population. And then we started looking at some distribution. Once again, went over the box plot. And then we tried to plot some distributions, especially for the age, and we looked at how the data is distributed. And we also looked at a different type of distribution, which was the histogram. Okay. Well, another thing maybe we could also look at before we jump into the statistical tests is maybe we could also, one of the other distributions we look at the last time, the scatter plot. And so we can actually, so to do the scatter plot, we can just do sns dot scatter plot. And then once again, we can bring in our data. So the reason why, sorry, somebody asking a question. Okay, I don't think so. So the reason why I usually like to use the SNS instead of going the matplotlib way is with the SNS, it makes things a bit simple. Even though SNS is built on top of matplotlib, it's a package that makes things a bit simple because the syntax is quite easy. All you need to do is give it your data, and my data that I'm interested in, for instance, is my subsample, which is the sample data. And then what I want to do here is I want to plot maybe a particular column against the other. Okay, so let's say maybe I want to look at the number of people, the age, the percentage age of people that fall within 12 and 29. Okay, let me put that on my x-axis. So what it's going to do is going to look inside this data and then pull a column name for me and then plot that for me. That's what it does. So age PCT 12 to 29. And then I want to plot that against Y. We can make it the other way around. I want to plot that against what are some of the crimes that we have in here. So we have murder, we have rape, we have robbery, we have assault. So let's look at assault, for instance. Assault per population, the rate of assault. And let's look at how that. So here we are going to, no, I'm in the wrong place. We're looking at Y being assault. And we can actually plot that to see how it's distributed. And over here, we are not seeing any strong relationship. We are seeing that the data is almost just everywhere. Okay, we can change this to maybe another column. We can just look at maybe some population column, and so we can look at the percentage that are white people in all communities, and then look at how they correlate with assault. So yeah, I've seen a lot of the data is here, and we are seeing some form of direction going here. But then one thing you can't see very clearly when you're just doing the scatter plots is that you can't actually see the direction. And so one other plot I like to use is what they call the regression plot. I know that one of the statistical tests that I should have captured or I should have taught during this session was the regression test. We did correlation test, but we've not looked at regression test. I've intentionally skipped that because when we get to the machine learning section, we'll be looking at regression. And so I just thought I'll cover it over there so that wouldn't be two things. So that once we cover it there, then we can also look at the regression test and then also look at how you can use regression for predictive analysis as well. So, but then you can actually do a regression plot as well. So what it does is that it looks at the regression between the two data points that you're trying to, and then tries to plot a regression line between them. So in that case, it gives you some sense of direction as to where the data is, how the data is related. So here we are seeing that there's some form of a regression line here. It's the same scatter plot, but then it gives you an additional information, which is the regression line, and it's telling you that there's some form of a negative correlation between the percentage of people living in a community that are white and the rate of assault by that population. And so what it tells you is that the higher the population, the lower the assault rate, and the lower the population, the higher the assault rate. That is what we are getting over here. That is what this is telling us. And of course, there are some few outliers as well that we can see from the scatter plot as well. But you can see a lot of the data is concentrated around here. And so one other thing that this scatter plot tells us is, like, if we recall what we learned from our lecture notes, we remember that it also gives us some form of information on the cluster. So I think I can pull Let's see if I can pull my PowerPoint slides so we just look at some of the things that we looked at concerning sorry, everything's misbehaving on this. Yeah. Let's see if we can look at scatter plot and look at some of the things we learned about the scatter plot the last time. Anyway, so one of the things that, like I said, it also looks at is the clustering. So you can see there's some clustering. It shows you that, okay, there are some few data points that are clustered over here, a few that are clustered over here. Maybe they are clustered over there because they may have some other, apart from the correlation or the relationship that exists between them, there are some other underlying facts that make those data points close to each other. And so you can see that there's a lot of data that are clustered here. There's a few of them that are also here and all that. And so one of the other things we'll be learning during the machine learning section is the unsupervised learning, where we can look at how you can give the model some data without labels, and then it's able to then look at the relationship between all the input data, and then cluster your data into various groups, and then also color them nicely so that you can see that, okay, this cluster belongs here, this cluster belongs here, and that is because the data sets have some form of relationship based on the distance of the data points from each other. So we'll be looking at k-means, and then you look at what k-means is all about and how it works. So let me see if my PowerPoints have loaded now nicely, and then we can, yeah. So, yeah, one of the things I mentioned was the fact that if you look at scatter plots, it's also able to show you subgroups that exist within the data or clusters, and also shows you outliers as well. And so, those are some of the things we are seeing over here. So we are seeing some outliers. We are seeing a very strong cluster over here of data points, and we are seeing some of them that are all over the place as well. All right, so that is that for the scatter plots. So let's dive into statistical tests. So just to recapture what we've been looking at in the area of statistical tests, we looked at some non-parametric statistical tests, and then we look at some parametric ones. And some of the assumptions that we looked at for the parametric ones is the fact that they always make some assumptions. And I think a lot of the assumptions I did not bring in the slides. I think I'll have to update my slides because after doing some reading again over the weekend when I was trying to prepare this, I realized that I missed out on some few things. So one of the things is that apart from the fact that the data is assumed to follow a normal distribution, there are also some assumptions that the data is supposed to have some form of homogeneity in there. So the standard deviation or the variance between each data point are usually expected to be the same. So that means the data is not supposed to be very widely dispersed. They're supposed to be close to each other or have a uniform standard deviation. Let me see, what else did I capture from I had some notes over here. Yeah, there are quite a number of assumptions that they make. Yeah, but that's just a few. So they have to be homogeneous, or you must send, and they're actually statistical tests that you can actually use to test if your data set is homogeneous or not. Whether they follow, whether they've been sampled correctly, or whether they follow a normal distribution as well. That is when you can run some of these tests and get some meaningful outputs. But some of the tests we look at are t-test. We looked at ANOVA and then we looked at chi-square. So today I think we're going to be looking at t-test and then ANOVA. And then if we have time, we'll look at chi-square as well, and then also look at time series analysis. But if not, then I'll just spend maybe the first 30 minutes in the next session just to look at those chi-square tests and how to do those things. And then we jump into machine learning, because next week is going to be dedicated to just machine learning. We're trying to finish with data analysis today. All right, so statistical test, t-test. So what does t-test do? T-test usually compares the mean of two independent groups or a single group to a hypothesized value. Okay, and I've tried to explain this, that what it does is that if you have data from two different groups, and you're trying to ask yourself some analysis questions like, so when you take on the average, so we can take our crime data for instance. On the average, how different is assault, right, or assault, the rate of assaults in New York compared to Los Angeles? So those are some of the hypotheses I've stated over here. That is what we are going to be looking at. So on the average, we're looking at some crime rates that have been reported in one state and try to compare it to some other states, trying to compare the means to see if there's some significant difference between them or there is no significant difference. They're the same. So whatever the rate at which this assault is reported in New York is the same rate at which it's being reported in Los Angeles as well. Or you're trying to look at the alternative where there's a difference. And so that is what we are just trying to see how we can use statistics to answer those questions. And when it comes to the t-test, there are three types. There's a independent sample t-test. Well, another thing that maybe I should have mentioned is t-test. Another name for it when you're reading your literature is called a student's t-test. And I think it's called student's t-test because I think the person who postulated this whole theory or t-test, I think his surname was student, and so that is why they call the student t-test. So in other literature, you see the name student t-test or just t-test for short. So there's an independent, there's a paired, there's an independent where you're comparing two independent groups. So in this case, we are comparing, if we are looking at just New York, it's a state on its own somewhere. And then we're also looking at Los Angeles, also another location. And we are trying to compare. But the example over here is that there's a difference between the average exam between online and in person. I picked this from our slides. And then there's a paired one as well, where you're trying to compare the same group, but then let's say within the same group, you're trying to run some experiment, and within a particular group, maybe you're trying to test some medicine, right? That's the example that comes to me all the time. And group A, at the first test, you give them medicine A, they try it, and then you give them some time to rest for that medicine to wear out of the system. And after some time, you give them medicine B again. And then now you're trying to, and then once after you give them medicine A, you recorded some few vitals, right? And then you give them medicine B as well. The same group, you gave them the same medicine B, you also collected the same vitals. And so what you're trying to now do is you're trying to compare before and after, right? Or when you gave them medicine A and then also compare to when you give them medicine B. Another term that they use for that is A/B testing, for instance. And so then you can also use the paired sample t-test. And then there's a third type which is called the one sample t-test, which compares the mean of a sample to a hypothesized mean. And this is so in this case, we can still go back to our crime data, for instance. They have, for instance, if in case somebody had done some studies in the past and said that okay, the rate of assault in the US, in the entire US, is maybe 200 and something per person or 200 per population. So they've come up with that postulation. They've postulated that this is a particular hypothesized that this is a particular figure that cuts across the whole country. But then you have gathered some new data and you want to compare that new data to that existing hypothesis that somebody has done. That is when you do the one sample. So in this case, you have some new data that you've calculated or you've collected and trying to compare the mean of that data to just an established mean already. We'll try and see if we can look at that example. So let's run an independent sample t-test with our data. So with the independent sample t-test, if you remember some of the steps that we looked at in our notebook, in our PowerPoint slide, we looked at step one, which was to how to set your hypothesis. And in this case, I have already defined some hypothesis over here. And what I've done over here for the null hypothesis, I'm saying that there is no difference in the average rate of auto theft in the 10 most populated communities in New York and Los Angeles. What I'm trying to do here is that I've taken in our crime data is community based, and each community is within a particular state, right? So what I want to do is, what have I written over here? I don't know what I was thinking when I was typing this thing. York. Okay. So what I'm trying to do is I'm trying to test some hypothesis, right? I'm trying to see if you take the 10 most populated communities in New York and Los Angeles, is the rate of auto theft the same across those two? Okay, if you take the 10 most populated states and the most populated communities in New York, and you take the 10 most populated communities in Los Angeles, is there a difference in the reported rates of auto theft? And then we look at the alternative. The alternative here, is there a difference? The main hypothesis is that there is no difference, because usually what happens is that for the null hypothesis, you actually always state that there is no difference. That's the first assumption. So if you look at the example that I put over here, or the notes that I've written over here, the null hypothesis typically states that there is no significant effect or difference between the groups. That is how you always declare your null hypothesis. Then when you move onto your alternative, that is when you then state that there's some difference, and that is what you're trying to test. And the rule over here is that when you test it, you're always trying to come up with a value or a central value that would help you explain or make a decision on that particular test. And that value, like we said, is the p-value, or also known as the probability value. In some cases, it's also called the alpha. Yes, is someone asking a question? Okay, I don't think. All right. So when you run your statistics and you get a smaller p-value, what a smaller p-value suggests is that it suggests a stronger evidence against the null hypothesis. So if you calculate and you get a p-value that is small, what that means is that when you get a p-value that is small, what that means is that you have to reject your null hypothesis, because there's a strong evidence against your null hypothesis that there is no difference. So a smaller p-value indicates that there's there's some significant difference, and then a larger p-value suggests a weaker evidence against the null hypothesis. So in that case, you stick to your null hypothesis because your evidence is suggesting that there's a weaker, or your p-value is suggesting there's a weaker evidence against it, and so you stick to that. So the rule here is smaller p-values, you reject the null hypothesis. Larger p-values, you accept the null hypothesis. Now, a commonly used significant level, or sometimes they call it the alpha value of that p-value, is the 0.05. This means that if the p-value is less than 0.05, we reject the null hypothesis with a 95% confidence level. Okay, that is what it's basically telling you. But then I've also stressed on this, and I want to stress it here again so you understand that the p-value or the alpha value, the 0.05 that I'm showing over here, is not set in stone. It's not the standard value. You can choose a different significant value based on your study or your study specific requirements. And one example I gave is that if you're doing in some scientific disciplines like physics, if you're running a t-test using, or you've collect, or you're working in the domain of physics, that's the part of science that deals with a lot of those physical stuff, and also those mechanical, and a lot of those complex stuff. What you need to do is that in that case, then the alpha value is not 0.05, but then they use a smaller alpha value, so you can go beyond the 0.05, because for them, what they want to see before they assume that the null hypothesis does not hold needs a higher confidence level. And so they reduce that. They reduce it. So in other studies, in some studies, it might even come up to 0.1 based on your study. So the first thing we need to do when it comes to doing the t-test is to prepare our data. So in this case, I said we were going to be looking at the hypothesis that we set for ourselves is what? Auto theft. And so we have to prepare our data to look at that. So we need to sample data to look at the auto theft. Somebody's joining. Some few people are joining. Okay, so But we are looking at auto theft in two states. We are looking at New York and Los Angeles, right? And so we need to create our filters. So let's say NY filter, unless maybe I'm doing this because I want people who are now coming to understand this whole Python thing too. I could just straight ahead go on and to put my filter in there and then run it, but then I'm taking it step by step so people understand. So I'm just creating a filter for NY for New York in my sub sample. So I'll say dot state, or just to make it standard for everyone to understand, I'll say state equal to NY. So in this case, it will give me a true or false mask or filter, which I'll then use. And then I'm trying to do the same for Los Angeles as well. Okay, so let's do the same for LA filter, which is going to do LA for short. Okay. Now the next thing we want to do is we want to then filter our subsample, and then we are saying that we are looking at. Sorry, I'm coming. Just give me a few minutes. We are also looking at the top 10 communities, right, with the highest population. And so what we need to do is we need to first of all filter our data, and then look at the top 10 communities in that data. And then what we need to also do is do that for both states, and then we can go ahead and run our t-test. So data preparation, we are still on the data preparation stage. And so what I'm going to do is I'm going to call this auto theft. Let me call it a data frame df for short. And then that one I'm going to say sub sample. And then I would say I'm going to filter let me run this. Some sample, bring my filter in there. Okay, and then I'm going to do a sort by sort values by the column population, and then I want it in I want top 10. So I'm looking at an ascendancy. I'm trying to look it from the top, from the highest value to the lowest, and so I would say ascending is false, right? Ascending is false, so that I just look at the. So what I'll do is I'll just look at auto theft df. So this is it. And so first of all, the state that we are looking at is just New York. So you can see it's all NY, and these are the communities, right? We have New York City, we have Yonkers City, we have Greensburg Town, Utica, and all the things, right? And we've sorted it. And so New York City has like the highest population, followed by this one, followed by this one. But then I'm just interested in the top 10. And so what I'm going to do is say, I'll just do a head over here and select the head 10. And so in this case, then I'm just taking the first 10. But let's run the same thing for, no, I have to rename this to NY. Because we have to do the same thing for LA as well, for Los Angeles as well. In this case, we are going to use the LA filter here, and let's look at the LA as well. Hopefully, I've done everything correct over here. If I run this now, so this is for LA. So New Orleans City has the highest population, followed by Baton Rouge, and then some other places. And so yeah, these are the ones I'm interested in. But then for all the cities, I'm just interested in the column that has to do with auto theft. So I'm just interested in the auto theft per population. So to do my statistical test, let's see. So the next stage over here now is to derive your p-values, right? To calculate and derive your p-values, and that is what we are going to do now. But then to do that, we will need to use a particular Python library. There are a number of Python libraries that we could use. There's the SciPy. There's the SciPy Python library, which you can use for all forms of statistics and then also all forms of scientific computing, right? It gives you all, in fact, a lot of the packages that you see us using, pandas, numpy, everything, are all built on top of this thing because they have all those mathematical algorithms in there that you can use for basic mathematical. So you can actually use it for all your statistics as well. There is also another package called the stats model. The stats models, yes, this one. It's also a Python package. Unlike the SciPy that is for scientific computing in general, this one is mainly for statistics, and so you can do a lot of your statistical testing here. You can do your regression analysis, you can do your ANOVA, you can do your t-test, you can do all those things in here, and even more. You can do them in here, but then and whenever you run your analysis, it gives you a nice table over here of all the statistical calculations that is done. So your F statistics, your R squared, your AIC, your BIC, and all those things. Yeah, it gives you all those things. And then there's a new one that came up recently that I like to use because it makes things very easy I always like to do the easy stuff. And so there's a new one that is called, I think, is it Penguin? That is what we'll be using today, actually. Penguin, yes, I think I've looked for it before. This is it. Penguin, I discovered this during my school days. A friend of mine introduced it to me. It's called Penguin. It's one of those other packages that you can use to do a lot of the statistical tests, but then it's based on pandas a lot. So it uses pandas and also uses stats model and also uses SciPy. So they brought all those two packages together into this one, and so it uses a lot of those their functions in there. And then it makes it very simple to use because just like I was using SciPy to plot, this one makes things a bit simple because all you need to do is call a particular function, pass in your data frame, and then it does your thing for you and then gives you your output. So if you go and look at the functions, you're interested in maybe ANOVA and t-test, you can come and look at the t-test that we are going to run, for instance. It gives you the function, everything that goes in there, your x, y, whether you want it to be a paired, and all those things. And then it outputs the t-value, the degrees of freedom. And these are things. And then also gives you your p-value, which is what we are interested in. And it tries to explain how mathematically that has been done and then gives you an example of how you can actually run it. So in this case, it's very simple over here. So if you look at this particular chunk of code that is over here, for this one is running a one sample t-test, which is one of the examples we looked at where there is an established hypothesis that you want to compare your data to. So over here, you see that they had some data over here, which is they've collected some data, which is the X 5.5, 2.4, and all that. And then they had some particular standard value, which is 4, right? So that is the hypothesized value. And I'm trying to compare the mean of this new value to this one. And that is a one sample. And so they just call the t-test from Penguin, run that and said the output should be rounded to 2 decimal places. And then it gives you a nice data frame with all the other thing that is calculated from the test. And then for us, we're interested in the p-value. And so we just look at the p-value and then based on that, we make decision on our hypothesis, right? Or if you as a scientist are interested in any of these other values to help you explain further your statistical test, then you can go and read more about what all these values mean. And then you can use them to actually back your explanation as well. And then when it comes to the t-test, when it comes to the paired test as well, you can actually just the same thing. So you can actually do your pre, which is the test before, and then the test after, and then you can also put that. And then in that case, you need to state that you're doing a paired test, which is true. And then it goes ahead to run your analysis for you as well. So let's go and look at this. Let's go and look at how we can do this for our data. So we are going to, in this case, we are going to be using the Penguin, which, like I said, makes things a bit easier. So I'm going to import. I've already installed it in my environment. So Penguin. We're going to give it an alias PG so that we can just use PG for everything. And in this case, my t-test result is going to be pg dot t-test. That's how they call it, right? It's t-test. And then let's see, what does it take? It takes x, y. In this case, I'm not doing a paired, and so I would say paired is false. And then I'll just leave it as it is, and then we'll run our test and see. So in this case, our x is going to be equal to our auto theft New York, and in this case we are interested in a column called auto theft per pop, and then we can just say we want the values. So let me just explain this to you. Let me just explain why I'm choosing to use the values at the end. So we're going to use what we call just the values. So if I run this, what it gives me is a series. Okay, it gives me a series with all the index annotations or the index numbers or the row number that each data point. But then I'm just interested in the values over here and not their indexes. So what I need to do is I just have to say dot values, and it gives me a nice array of just the values that I want, and that is what I pass to my t-test, and then it's able to run that for me. So that is why I'm using the dot values over here. Just for clarification, I just ran this just for clarification. One other thing you can do is I can just say from values, I can then send it to, or even from the series, I can just say to list, and then it gives me a list of values. But I'll just use values for now. And then our our y, in this case, is going to be auto theft LA. We're looking at the same thing. So when we run this, and then we come and look at our t-test result, should give us a nice table, and we have a p-value here. So in this case, our p-value is greater than 0.05. So based on what we've learned so far, what is that going to be then? I don't know if anyone can unmute and try and explain to us. Any top statistician amongst us who can explain this for us? I'm waiting. Is there any top statistician amongst our class that can just explain this? So we can say our sig level is 0.05. But
No
nobody wants to.
significant difference.
Sorry?
The p-value showing 0.06 is
Yeah.
greater than the 0.05 threshold. So there's no significant difference between the two groups.
Okay. All right. And that is what we've learned from here, right? That if the p-value is, but then our null hypothesis, our p-value is bigger. So it suggests a weaker evidence against the null hypothesis. And our null hypothesis says there is no significant difference. So a larger p-value is saying that there's a weaker evidence against the null hypothesis. So in this case, we have to be rejecting the null hypothesis.
Are we rejecting?
Yes.
But that's 0.06.
Which is a larger p-value compared to our alpha value.
Yes. So when it is less, we reject. When it is greater, we accept.
Okay.
Because the 0.06 is greater than 0.05. We're using the p-value to compute, to make decisions. Yes. If
Okay.
that was less than 0.05, then we will have been rejecting the null and accepting the alternative.
Okay. All right. Anybody else with another opinion? Okay. Yeah, sometimes these things can be a bit confusing, but then
No, it's very clear. If
it's
we're
very clear,
using
right?
the there's also the alternative. There are two rules of thumb: either using the p-value, the critical p, which we are doing now, or
Okay.
using the calculated or tabulated.
Which
Now,
one?
there's another rule of thumb: using
Uh-huh.
the calculated value against the critical value. So
Okay.
what we have there, minus 1.95.
Yeah, is the actual
I'm
T
I'm
T
trying.
T value.
Yeah, I'm trying to open my table, the table of distribution. So that can also
Okay.
confirm
Okay.
when the calculated value, if the calculated is less than tabulated, we accept null hypothesis. If tabulated is greater, we reject. So that will confirm whether the p, what we said was correct. I'm just trying
Okay.
to open my system
Okay. All right.
to get the table. So the degree of freedom, very
It's
tiny here.
it's 18.
Okay, is that 18?
Yes, 18.
18. Okay. That's the limit.
Okay. Can I say something? Hello. Yeah, hello. Your thing is a bit noisy, please.
You hear me now?
Yeah, I can hear you.
Okay. The p-value of that 0.0065. Am I got 0.0065 and 06 something?
Yeah.
Indicate that the result of a statistical test are statistically significant. This means that the probability of getting the observed result by chance is very low. So that is what um, I'm getting better. Let me check something first.
Okay, I've opened my table.
Okay.
Now at 18 degree of freedom, the tabulated or critical T is at 0.05 is 2.10. So the rule of thumb is if calculated value, that's this value now, we are going to
Uh-huh.
ignore the negative sign anyway.
Yeah.
So 1.95 is less than 2.1. So
Okay.
if calculated value is less than tabulated, we accept the null hypothesis that there is no significant difference between the two groups. But if
Okay.
it is the other way, we reject. So in this case, it is less,
It
which
is
which
less
further confirms the p.
with a
For
P.
p, the rule of thumb, if p is less than or equal
Then
to 0.05, we
5.
reject,
Check the null.
meaning there is significant difference. But when p is greater, we accept that there is no significant difference between the groups. So using the calculated versus tabulated or using the p confirm that there is no significant difference between the two groups at
All
two
right.
tail tests.
Okay. So just for clarity, can you just go over that again one last time so that everyone would understand?
Okay, I said there are two rules of thumb.
Yeah.
The first one is using the calculated value versus the tabulated or critical value. And that
Yes.
rule says if calculated value, it doesn't matter whether it is T, whether it is F, whether it is R, it cuts across. If calculated value is less than tabulated value, we accept null hypothesis.
Okay.
Then if calculated is greater than tabulated, we reject null hypothesis. That's the first rule. The second one is using the critical p-value. The critical p-value, the rule says if p is less than or equal to 0.05, we reject the null hypothesis. If p is greater than 0.05, we accept the null hypothesis. So either of the two can be used.
Okay. And in this case, after calculating this, the p-value is greater than 0.05.
Yes. So we are going to accept that there is no
No
significant
significant
difference between
difference.
the two.
Okay. Thank you very much for that. Has anybody else got any question? All right. So let's run the same thing again, but this time around, let's assume that there has been a standardized or a hypothesized mean that we want to compare just, let's say, New York to. So in this case, we want to compare to the fact that there's some standardized rate of auto theft, as the rate of auto theft per population is per 100,000 population is about 200.8, for instance. In this case, we just want to run. In this case, we are doing the one sample t-test. This one. In that case, have you seen the the attendance form? Okay, yes. I think I've sent it. Those for those asking. In that case, we can just run this again. Let's call it our. Let's just rename the variable and then let's see what we get. Yeah, so this is just a hypothetical thing that I've done. There is no established mean, but then I'm saying that if, in case you also want to compare the mean of the auto theft in that top 10 communities to a certain standardized or hypothesized value, you can also do that by just putting that value over there and running your thing against it. And it also gives you your value, and then that you can then use to then also make a decision about whatever hypothesis you have declared. All right. So moving on. So what I'll do at this point is that we're going to take some 10 minutes break. And then when we come back, we'll dive into ANOVA. Okay, we'll look at how you can also do analysis of variance using the same Python package and how you can do these things with Python as well. Is that okay?
Yeah, it's okay.
Yes, sir.
All
Yes,
right.
sir.
Okay.
Hello.
Yeah, hello.
Hello. Yeah, we're here.
I can't hear anything.
I can't hear anything. I can't.
What do you mean by you can't
We
hear
we are
anything?
we are we are for, we are in break for like 10 minutes.
We are on
Okay.
There's
break
a ten
now.
minutes break.
Okay. Thank you.
Mm.
All right.
Okay. For those who are saying they couldn't hear anything, because we're on some few minutes of break. I hope you can all hear me now.
Yeah. Yes, we can hear you. Thank you.
All right, great. Okay, so before the break, we were looking at some statistical tests. We just finished trying the t-test and how you can run the t-test, how you can prepare your data and run your t-test, and how you can explain the some of the statistical results that you get or the test values that you get. So we looked at one of our colleagues was kind enough to take us through how to use the t-test to explain what your results mean and how you can also use the p-value. So the next thing we're going to look at is also look at another form of statistical test which has to do, whereas t-test enables you to compare two, what if you want to compare more than two groups, or you want to assess some significance between two or more groups or three or more groups, for instance, then in that case we use what they call analysis of variance. There's also a statistical tool that is used to determine significant difference between the means of three or more groups. And with a statistical test, there's a one-way ANOVA and then also there's a two-way ANOVA. With a one-way ANOVA, what we are trying to look over here is to compare the means of three or more groups to assess if there's a statistical significance between them. The scenarios where you might want to use this, the examples that came from the notes that I was using to generate this slides were if you might want to compare maybe the average growth rate of a plant under different fertilizer types, right? 3 or more types. So you want to look at the growth rate, which is your dependent variable, and you're trying to look at some different fertilizer types. And so then you can bring different more fertilizer types and then compare it to that to see how, if there's a significant difference between the different fertilizer types and how they affect your growth rate. So in our case, we can also consider one factor in an example, age, and then look at its impact on some dependent variable. So let's try and look at an example. So you usually use a one-way ANOVA test if you are only interested in the effect of a single factor on the dependent variable, on a dependent variable. So a single factor on a dependent variable. And then for the two-way, I don't think our data can be used for two-way, but then the Penguin package comes with an example data that we can use to test the two-way as well. So as usual, we'll set a hypothesis, and then secondly, we'll look at our data that we're going to use. So in this case, usually the data has to follow some specific, the data has to be set up in a different way. So we'll look at how we can do that. So here we are trying to look at, we are comparing assault, right? We're comparing assault in the 10 most populated communities again in New York compared to Los Angeles and Florida. So here we're looking at 3 different states. We are comparing New York to 2 different states, right? So in that case, what we need to do is run our filter again, but this time around we can bring in, we have to write another filter for Florida, for instance. And so we'll create an FL filter here, and then that would be the same thing that we were doing up there, but this time we're looking at subsample of state state equal to, I think the annotation they use for Florida is FL. So I see that the number of attendants went up to 50, and as soon as I shared the attendance form, it has dropped to 46. So some of you just come to fill attendance form and then you disappear again. Okay, interesting. All right, so what we want to do here is we have to create a whole data frame, and so we'll just create a ASLT DF, which is going to be an empty data frame in this case. So we'll do a PD, because the way we need to pass the data for ANOVA is different from the way we needed to pass it for the t-test. And so I'd have to, first of all, filter all the data that I need, create a new data frame, and then restructure the data frame in a way that the ANOVA would ANOVA function in the Penguin would understand before we run that. And so we'll create an empty data frame, and then over here we can bring we can create an assault NY, which will not be too different from what we're doing over here. So we can take this whole thing again and bring it here, but the only difference here is that we will be looking at yeah. So we're going to filter for, we're going to take the top 10 for this. In fact, we could have just used the same, but then let me just separate it. So there's LA, then there's FL. And then over here, we're going to use the LA filter here, which we already set up there. And then here, we're going to also bring in the FL one that I've already set up here. So if I run this and if I take my assault for Florida alone, it should have just FL state, yes, and the top 10 of that. And the highest populated community is Miami City in Florida. And then the top 10, the highest is Miami, and so yeah, so we have that. But what I want to do is to create pass all this into a data frame. And I want to pass that into this data frame. So what I'll do is I'll just call this data frame here, and then maybe give it a column. So I'm going to create a new column in that empty data frame called NY, for instance. And then I'm just going to pass the values for assault per population here, dot values. And I'm going to repeat that for LA and Florida. And so for LA, so here I'm creating a new column called LA, and that one is going to take the data frame for the LA, create another one for FL Florida, and then take just the assault from FL as well. So if I run this and everything runs successfully, then what I need to be, what I'm expecting to see from my ASLTDF is a nice data frame that has 3 columns, NY, and these are just the top 10 assault rate population for those top 10 communities, right? But let me just show you an example of what the ANOVA. So whenever you install PG, it comes with a sample data set that you can use to test your analysis or test the package. And I think there's a package and there's a function in there called read data set, and then we can say ANOVA. So this would give you an example. So this is an example data set, and you can see that with example data set over here, they don't have everything in columns, but they rather have one column. So in that case, they have one column that has all the, in our case, we need to create a column that has all the states. And then we need to actually merge all these things into one column, which is going to be just the values, right? And then for each value, we have the associated state with it in this case. I hope that makes sense, right? So we need to convert our table into this state where we have the states being here. So we have NY, and then we have the corresponding value NY, and then we're going to have FL corresponding value LA and the corresponding value. Here they have the light blonde, dark blonde, light brunette, dark brunette. So that is what they were trying to do there ANOVA for. So to get our data in this state, there's a function in, or there's a method in pandas that we can use, and I think it's the melt method, right? So what we can do is we can, how do I do this? We can say assault df tr or trn, which is trnf transform, and then we can just do as ltdf. Then we are going to call the function called melt. So we're going to melt the table. That's the term they use. But what this is going to do is that, so for melt, let's see what does it take in. So for melt, we don't need all this, but what we need is we need to give it a variable name for the vars, and then the variable name for the var name, one of these columns. Let me see. Yeah, so let's just say var names. So here we are going to melt the table. So let me just explain to you what I'm doing before you, so people do not get confused. So if I run this melt without put in all those variable names over there. It's going to create a nice table for me. So you can see it converts the table into that state where it takes all the NY and then takes all the NY values, take all the LA, everything in just 2 columns. You get it? And then Florida, everything in 2 columns. But what I wanted to do while I was passing those other variables is that I don't want the NY and all the states value of column to be called variable. And I don't want these values to be called values. So I wanted to just change the column names. And that is what I was trying to do over here by saying, so the variable names is going to be var name. So I can rename that to states. And then I can say my value name, which is the value name is going to be, I can call that ASSALUT, assault, right? So assault rate, for instance. So if I run this again, then I have a melted table that has, the appropriate column names. That's basically what I was trying to do. So then the next thing I want to do is the next step in, after preparing the data, the next step is to calculate or run your ANOVA itself. And so for that one, we're going to call this AOV, so analysis of variance, AOVDF, or the results, right? Let's call it AOVRES. And then we're going to call the PG ANOVA. That is the name. There is also the ANCOVA as well. And then in the ANOVA, what we want to do is we want to give it our data that we want to use for the ANOVA. So our data in this case is our ASLTDF transformed, the transformed version of it. And then remember, it's a dependent variable, and then we are trying to compare it to some other variables. And so our dependent variable in this case, so when you look at the ANOVA column, there's a DV, which is a column name in the data containing the dependent variable. And then between is a list of other variables that you want to, the name of other columns that you want to run your analysis on, or the column that you want to run your analysis on. So in this case, our dependent variable is the values over here, and we want to compare the various states. And so dv is this dv dependent variable, sorry, is going to be the assault underscore rate, and then the between is going to be the other. So we're going to compare these values between the states. And so in that case, then this is going to be states. And this makes, and then what else am I supposed to put in there? If I run this, let's see, is there any other argument that I'm supposed to put in there? If I run this, let's see the result that I get. So AOV results, let's look at it. It gives us the, let's try and see if we can, let's see, detailed. Let's set detailed to true. So it gives us a detailed, yeah. So, but then once again, the values are a bit too big, so let's round it to 2 decimal places just to get some. Okay. So this is the output of the ANOVA that we've just run. Let's make it 3 decimal places because we are getting some very low p-value over here. Okay. So once again, this is what we have. And as you can see, we are getting we are in this case, it's giving us two statistics, but then it's not giving us p-value for this f, the p, and in this case we are getting a p, u, and c, and this p, u, and c is actually supposed to be. Let's look at the ANOVA again. I think there's a corrected p-value and there's a p-value and there's an uncorrected p-value. That is something I need to refresh my brain on. Yeah, so there's an uncorrected, yes, and that is what it's telling us. So what it's calculating over here is the uncorrected p-value, and I think it's p-value that has not been adjusted. So is this something that Olufemi, is this something you can explain to us?
Yeah, this is very significant.
Okay.
Now the P actually, we are more interested in the first line where you have the P value.
Yeah.
Because actually the sum of
First
square for the first one divided by the degree of freedom of P gives us the mean sum.
Okay.
Same thing. So the mean sum of the one up and the mean sum below gives us that F, which is 6.673.
Yeah.
That's the calculated F.
Okay.
But if we check, I've checked it against the table. It's
The table. Okay.
3.2. Since the calculated here is greater than the tabulated, it shows a significant difference. We are going to be rejecting null hypothesis.
Okay.
Then if
Yeah,
we are
because
using
the p-value is very
the
tiny.
very low too, so it's obviously very significant. So
Yeah,
both of them.
but then the p in this case is the uncorrected p, which I know has not been adjusted. I think they usually adjust it. In some cases, if you are running, I think multiple samples, if you're running multiple tests and they put all the p's together, they usually adjust them to a particular value. But then if in this case the p has not been adjusted, and so it gives us what they call the uncorrected p, which is not too different from the adjusted one.
Okay, yes, and it's just a one-way ANOVA.
Yeah, just a one way ANOVA. So yes, so the p value
Need
here can
for
still be used. Sorry.
there's need for a further test, a post
Yeah.
hoc test
Okay.
to confirm where the differences actually lie between
Yeah.
the states.
Okay. So that is a one way ANOVA, and these are the p values. And based on these p values, then you can go ahead and either accept or reject your null hypothesis. And like he said, the main thing that we are looking at is the significant difference between the different states. And so this is the first line that we are interested in. But I think if we move on to the two-way ANOVA, then we'll also be interested in the within as well, where apart from just giving us the significant differences or the variations between the different states, it also gives us a p-value for within the value itself, right? So if you take New York, for instance, are there any significant variations within New York itself, the crime rate within New York, or the assault rate within New York itself? And if we had, so in the case of, in the way our data is structured, we don't have a second sort of level that we can use for a two-way test over here. But then let's go ahead and look at, we can still do a two-way ANOVA test. And then let's use let me just consult the Penguin. I think Penguin has some example data that you can use. So this is the one-way ANOVA. I remember when I looked at this, there was a two-way ANOVA. Yeah, so the two-way ANOVA with balanced design. Yeah, so in this case, their sample data that they give is ANOVA 2. So let's quickly run this and then get the example data and then use that to also test. So let's run this quickly. So this is going to give us some data. So in this case, it gives us a data where they're trying to look at some yield values, but then yield values for a particular blend of I don't know whether this is a fertilizer, but then a particular blend of fertilizer for wheat, and this is the yield. And then there's another blend Y for those same crops. So in this case, we are comparing these values between, we are looking at how this and this affect the yield, and then we're also looking at how yield is the difference in the yield within blend X within the wheat itself, right? We are looking at the difference between this, and then within this itself. So in that case, we can just do a head over here just to have a head over data, and then we can go ahead and then see how they run this. So in this case, yeah, so in this case, we're running the same ANOVA, but they're looking at yield and then between blend and crop. And so we'll just replicate the same thing over here. So we'll look at a ANOVA AOV2, AOV2, AOV2 result, and then we'll do a PG ANOVA. And then data once again is equal to, in this case, is equal to data, because that's what we'll be using. And then our DV is yield, and then between, we're going to pass a list of values, which is blend and crop. So we are going to run a two-way ANOVA for this. And once again, we also want a detailed output, which is true. So we run this, we look at the AOV2. And so here we're getting 3 lines. And I think the most significant ones that we are looking at, we are interested in this case, are the first 3 lines over here. So here we are looking at how yield differs for the blend. We're looking at the yield for the crop, and then we're looking at the combination of the two of them as well, right? Blend times or and the crop, and also looking at the p-values for all those. And so we have the uncorrected p-values for all those ones. So if we had set some form of a hypothesis, then based on these p-values that we are getting over here, we would either be accepting or rejecting those hypotheses based on all the values that we are getting from this ANOVA test. Right? I hope that makes sense. All right. So that is ANOVA, and this is how you can run your ANOVA test using Python. Like I said, there are various statistical packages or libraries in Python that you can use, but then I find Penguin much more intuitive and straightforward. It gives you your output in a much more simplified way that you can then, I mean, stats model is the best because, like I said, Penguin itself is based on the stats model, and the stats model also gives you quite a lot of outputs which you can pick from. But then sometimes I think it's a lot. It gives you a lot of things, and so it becomes difficult. But then if you know what you are looking for, if you are interested in the F statistics and maybe just your R squared, you can straight go to that and look at the value and then use that to make your inference or your conclusions or your decision. So it's another package that you can test and see. It's also equally good. It gives you a lot of outputs that you can use to make more. Gives you more information that you can use to make inference about your statistical test or about your data, or more values that you can use to explain your results. And of course, all these ones are also based on SciPy. So when you go to the documentation of SciPy too, but SciPy has a lot more that it does. It's not just for statistics, but then you do a lot of other things. And so here you're looking at Fourier transform and things for time series and all that. Okay, so that brings us to the end of statistical tests. Like I said on Wednesday, I won't dive because the data we are using here is not categorical. I won't dive into chi-square today. I'll bring that one. Like the first 30 minutes, we'll just look at the chi-square test and then we move straight into machine learning. But one thing I wanted us to look at before we close for today is time series data, because I did talk about the fact that I was going to show you how you can also load in time series, how you can visualize your time series data, and how you can actually run some analysis on time series as well. So let's just look at that. That'll be the last thing we look at for today, and then if we have any questions, we can ask, and then we can move on from there. So time series. So for the time series data, we'll be looking at satellite data that I have transformed into a nice DF or nice data frame or into a nice table. So what I've done is let me see if I can pull out one of my papers and then just show you what I've done. Show you what I've done. So let's see. I think I have. Let's see which one is this. Which one is this? Yeah. So this is one of my papers that published about 2 years ago. And so the data that I'm coming to show is based actually on this paper. Wait a minute. Why? Someone says. Okay, all right. Please, yeah, please. You're free to leave. If you have another class that you're teaching, you're free to leave. Thank you very much for your contribution. Much appreciated.
Thank you. Thank you very much.
Okay, so with the time series, no, it's not showing a very good example of what I wanted to show. Uh, okay, just give me a minute. Let me just pull the right version of the paper out from the internet, and then I'll yeah. Okay, so I just want us to look at this diagram carefully. So this is like the map of Kenya, and before
Pulling the eye out. Contact lens.
before I move on to the data, I just wanted to explain some few things for you to understand. And so this is Kenya, and Kenya they have boundaries, right? They have there are various regions that make up Kenya. So we have the Nairobi, we have like Laikipia, we have Samburu, we have Turkana, we have all those places. And then there are also existing maps that show the various agroecological zones, right, within Africa. And I've just cut the agroecological zones for Kenya. And so here, when we look at this data, for instance, we are looking at the red area shows you where there's the arid agroecological zone. The green area shows you the light green. So they show you the various agroecological zones. So there's a very deep green one that shows you the arid, and then the light green one shows you the humid, and then there's the semi-arid. And so all the colors over here show you the various agroecological zones. So what I did was to actually then download satellite images over the entire length and breadth of Kenya. And then for those satellite images, I sampled them based on these agroecological zones. So if I pick a pixel from Wajir, for instance, I know that within Wajir there's a very arid zone which is red, and then there's also there's a small zone here which is arid, and then there's a small zone here which is semi-arid. So that means we have very arid, arid, and then semi-arid. So I sample all the pixels within the arid and find the average of that. Sample all the pixels that form part of this region, find it, and then also sample all the pixels that form part of this region. So when I then sample that over a number of years from that satellite, I'm able to generate some form of a time series. And this time series is what I'm going to be showing you over here. So let's call a particular package called let's import what they call the globe, and then we're going to look at the files, and then say globe. So glob is a package that we use to like pull in files from different directories. So there's supposed to be a directory on here called modus data Kenya, and then I'm trying to look for everything that ends with CSV in there, and so this should give me all the files that I have in there. So these are all the files that I have, and these are all files, CSV files that I've used to extract data from, or these are all the files that show data that have been extracted from the satellite images based on those boundaries that I showed you. So first of all, I actually segment on the region. So if it is Turkana, for instance, we'll be looking at data from Turkana. If it's a Turkana region, I look at that whole region, and then within that region, I pick pixels that represent very arid, arid, and semi-arid. All right, and so what we can do is we can just say Turkana TURDF. I just picked it at random because it's one of those very interesting regions that one of the regions I find very interesting in Kenya. So PD dot, so what I'll do is I'll just see PD dot read CSV, and then there we have modus, and then I have S2 underscore TURE. Yes, so that's the one I'm interested in. So when I look at the head of this data frame, so this is the data that we have, and this is aggregated satellite image or aggregated indices derived from satellite images. So I had a satellite image that was giving me rainfall data. So you can see this is rainfall data, aggregated rainfall data. So I found the mean rainfall data for that semi-arid region in Turkana. I also looked at the average soil moisture from another satellite product for that same semi-arid region in Turkana for this date, 2001. So I have data from 2001 all the way to 2018. And then other indices that I calculated with that same calculated from other satellite products are the vegetation health index. I also calculated what they call the soil adjusted vegetation index. I also got the land surface temperature. I also got the vegetation condition index, which is all telling you about vegetation health. There's the NDVI as well that tells you about vegetation health. There's a temperature condition index, which was derived from the land surface temperature. And then there's a modified temperature condition index. So these are all just indices that we calculate from satellite images. And so what we are going to look at is we're just going to plot a few of this just to look at we're going to plot a few of this just for you to appreciate some things about the data set. And so we're going to do a line plot in this case because we are exploring this data. We'll look at the line plot and let's see, what can we do over here? I've already imported, so I'd say PLT figure, and then we'll do a fake size. This time I'm going to do a fake size of about 17 by 6, and then I'm going to call SNS dot. But even before I do that, there's one thing I need to check. I need to check if my time series, my date column has been read as a time series, has been read as a date column. So actually, the date column is object. It's not been seen as a date column. And so what I need to do is I actually needed to add one line over here whilst I was reading my thing to make sure that I convert the date column to a date time column. So date column, I'm going to say PD to date time. So PD to date time, and then say I want to convert this date column to a datetime column and pass it back to the datetime column again. So I'm just overwriting this column with a column that has converted all these values to a proper datetime column so that I can do my analysis with it. It becomes easier when you convert it to a datetime column. It becomes easier for you to say, okay, I want to pick 2021, or I want to pick 2007, 2008. You can tell pandas to do that and we'll do that for you. So it doesn't change anything, but the only time realize that this was initially an object, but if I run this now, it should change to a date time column. So it's now a date time column. So the package now recognizes that column as a date time column. And so then I can apply certain functions to it to select certain dates that fall in certain months, or select certain dates that fall in certain years and all that. Okay, so what I can do now is I can say SNS line plot, for instance, and the data that I'm going to be using is the Turkana data. But what I need to do is I need to let's see. Yeah. So Turkana DF. But then I'm interested in just a particular year. So I'll say Turkana DF date. So what this enables me to do is, because I've converted that column to a datetime column, I can call a special function within pandas that is called DT. And once you call DT on a date column, you can apply a lot of date functions, or you can do a lot of selections, date selections. So I can say DT, for instance, and I can say it should select every year that is equal to 2008, for instance. Okay, so in this case, what will happen is that it will look through that data and select only data that is equal to data that falls within the range or has the year 2008, and give me only that out of the entire 2001 to 2019. Because I'm using this DT function, I'm able to do that. I mean, just to explain that, if I come and run. So what I'm doing here again, I'm just doing the same filter that I used to do for, like when I was trying to filter out Florida or filter out, but just this time I'm filtering by date. And so when I pick this now and I run this, it gives me only, so if you look at it, it gives me only dates from January to December of 2008. I can actually come here and say I want DT of 2017, for instance, and we'll give it a 2017. I can actually say, okay, I don't want year, I want a month, right? And say month that is 6, for instance. Let's see what happens. So to give me from 2001 to 2018, but only give me data for all the June, all the data that falls in the month of 6, right? And you can come here, and usually if you do the DT, there are so many things that you get with the DT. So you can do day of the week, you can do day of the year, you can do day in a month, you can do hour if your daytime has some time aspect to it. So there's so many things you can select by. But in this case, we are going to just settle with year, say 2008. That's what we're looking at, right? So yeah. So then I select that, and then for SNS, I can say I want to plot, and for that I want to put a date column on my x-axis, and then I want to plot my NDVI. I want to look at a time series of the NDVI, right, for 2008. So then I can say y is equal to NDVI, and then what I can also do is I can say, because my data, if you look carefully at my data, I have zones over here, right, and I have time series from 2008 January to December for semi-arid. I have the same 2008 to December for very arid. I have it if there's, so let's see, in Turkana we have, in Turkana we can check the, number of agroecological zones that exist within Turkana alone. So I can do TURDF and say zone, and then call the unique function on that, and then will get me just the unique. So there's a semi-arid, arid, and very arid in this particular column, and so that's why we have a lot of data points. And so we have January to December for very arid, January to December for arid, and then January to December. So we have all those columns written in there. So I can then give my SNS a hue, and that hue I can give it something to filter the time series on. So I'll give it zone, for instance. So if I run this, it should plot, it should give me a nice time series plot or line plot of the same NDVI for the different agroecological zones because I stated hue. If I was not using SNS and I was using maybe just matplotlib, raw matplotlib, then I would have first of all, after running this year 2008, I would have passed this to another variable and then come and filter on the, come and run another filter on the zone as well, just to get a particular zone before I plot that. But with SNS, I can tell it to do that filtering for me before I plot, and so it gives me this. And so I'm just going to leave this on here for just 5 minutes. I want someone to just look at it and tell me what they think about how. So NDVI, if I haven't explained yet, NDVI is normalized, is a normalized difference vegetation index. Okay, normalized difference vegetation index, and what that gives you is that it tells you the greenness of vegetation in a particular area, or how healthy the plant is, or how green the plant is. And so what we are seeing here are the greenness of plants as time changes over time, right? And so if you look at how the health of plant is changing over time in the very arid, arid and semi-arid regions, what can you see? And bear in mind that NDVI usually ranges from between -1 and 1, but then anything below 0 is not plant. So everything above 0 has to do with plants or leaves or crops. Anything below 0 is non-plant, but then it's some water body or something that is not necessarily a plant. And so you can see that the NDVI values, you're not seeing anything that goes beyond. I mean, if at a particular point you see some of this data going beyond, it means that what is seen at that point, there's no vegetation. It's just seeing some bare soil or seeing some water body or something, or a cluster of water or something in there. So that is what this is telling you. So if you look at this time series Who can just unmute their mic and tell me what trend they are seeing in the time series? Do you see any difference between arid zone, semi-arid, and very arid? What do you think is happening to vegetation in the very arid zone compared to the arid and the semi-arid? Nobody. Okay. So what is happening here is that you can see that for the very arid, so very arid are actually areas that are very dry. You have very less rainfall falling in those areas compared to the semi-arid and the arid. So as you can see, vegetation health generally in the very arid are generally low compared to the other ones. So the vegetation health for these ones are higher compared to this. So that is what a time series is telling you basically. So just by looking at the data, you're able to see that, okay, in the very arid regions, vegetation health is very low. And in the semi-arid and the arid, where rainfall is a bit higher compared to the very arid, you see vegetation is a bit, vegetation in those areas are a bit healthier. So they're a bit greener. And then one other thing you can see in the semi-arid is that you're seeing some seasonal pattern over here that around around May, June, July, there's an increase and then it drops again around July, and then from October going it increases again, right? So we can ask ourselves, what do you think is affecting? Why does vegetation health go up around this time and then drops again? And you see that peak and you see the similar peak here as well, where for the very arid region it peaks around this time, and then you see some peak here, but then it drops again immediately. So what we can do is we can just do another of this plot. Let's look at how rainfall is also changing in the same area. So instead of NDVI, let's plot rainfall over here, right? Let me make this 5 so that you can run both of them side by side and look at them the same screen. Okay, so this is rainfall and this is NDVI. So these are the rainfall patterns in that area as well, right? So a high peak tells you when there's a high rainfall. A low peak tells you where there's no rainfall at all or very low rainfall, right? And you can see that for the very arid, and semi-arid regions. Do we see any patterns here? Do we see that when it rained, when the rainfall picked up around between March and May, when the rainfall picked up, then vegetation health also went up a bit around that time. It became a bit green. Right, when it rained at this point and also rained at this point. So you see that happen. And then when it stopped raining for a very long time, vegetation health significantly dropped in the arid region, right? So you can see that there's some correlation going on over here that as it rains, it positively affects vegetation, which is expected, which are some of the things expected. And then you can also compare other columns like the VHI and then also you can also compare that to the temperature and also compare it to the soil moisture. So one last plot maybe we can look at is also the land surface temperature, for instance. So we can look at the LST, which is land surface temperature, and this one is also measured by satellites in space. And so land surface temperature for that same area as well. We'll look at how let me just so this is land surface temperature as well. So you see the time series all over the place, but then if you look at the land surface temperature, in this case land surface temperature is still in Kelvin. I've not even converted it to, I think I've not converted it to degrees Celsius yet. I've not converted it to degrees Celsius. It's still in Kelvin, but then still telling us something. So one thing we can see here is one interesting pattern we can see here is that you see that for the very arid, temperature is mostly constantly very high, right? Compared to the semi-arid where temperatures are quite low, and then temperature increases around this point, but then drops again around this point. But then you can see that for the very arid, temperature is generally very high. You can see the green line. So these are some of the ways you can plot the time series and analyze them. One thing I wanted us to, you can see that, you can also see from this time series that the data is quite noisy, because you can see that at some points, even though there are some changes, you see that the peak is a bit rough, right? The peaks are a bit rough. It's not, you don't see that smooth increase in temperature and that smooth drop in temperature, but then temperature goes up, you see some jagged up and down switches, changes going on. And usually what we do after that is, then if you want to then look at how these trends are going and look if there's some seasonality existing in the data, what we usually do is to apply what they call the smoothing. Okay. And so one thing I wanted us to look at today was to look at how you can apply smoothing to your time series. But then I think time is fast spent now. But then if you're okay for me to just do some 15 minutes just to take you through how to apply the smoothing algorithm, just give me a thumbs up. Or if you want to hold back now so that we move it to next week, we can do that. Yeah, Leon, do you have a question or just, let me see from the chat.
Yes. Is it possible to use JavaScript?
JavaScript to do what?
This maybe to do some correlation between maybe LST and the NDVI.
So first of all, does JavaScript give you the tools you need to do that? That's what you need to ask yourself. I don't think JavaScript has the tools that you can use. Fine, JavaScript has some very nice plotting tools that you can use to plot this, but I don't know whether JavaScript goes ahead to. I don't know if JavaScript has some packages that you can use to actually analyze this data or apply this smoothing functions. Why do you ask about JavaScript? Do you have any experience in it?
Maybe I just 2 weeks back I just read this something like Google S engine. They can
Okay.
perform this analysis.
Okay. So yeah, if you want to use Google Earth Engine for such an analysis, then yes, you can. The Google Earth Engine, they've built it such that they've been able to put some JavaScripts in there that you can use to do your plot. So what you can do is Google Earth Engine, for those who don't know what it is a platform where you can actually go and interact with a lot of Earth observation data sets. So you can go in there, you can look at MODIS like I use in this case. You can look at Sentinel. You can look at all those satellite images, the free ones that come from the various satellite data providers. And if you know how to write JavaScript, you can interact with that data using JavaScript. So what it does is that you run the JavaScript in the back end. JavaScript then goes to run some scripts that will then pull that data for you.
Okay.
Yeah. So then you can use that, and then you can use that too. But then for me, yes, I mean, Google Earth Engine is good for doing these things, but after you have run everything in there to actually run some further analysis, the JavaScript that is on Google Earth Engine, I know over the years they've improved it, they've added some functionalities to it, but then I would say Python or even R has a lot more functions than the JavaScript that they put in the Google Earth Engine. So sometimes it's good to actually you go and download the data yourself and then run your own analysis on your system using Python, because you then have a lot more tools to play with. Okay, so I see people are saying we should pause it over here and then move to next week so that you can digest whatever it is that we've covered here today. If that is fine with everyone, then we can end the class today. We can end the class here today, and then from next week, what we'll look at is we'll First 30 minutes, the smoothing function is not a very long. I already have all the functions written. All I need to do is just pull it here and then run the smoothing function so that we can smooth out the data just to see the trends in there. And then we would also look at some categorical data sets and how you can use chi-square to also run some statistical tests as well. Is that okay?
Yes.
All right.
Yes.
All right. Okay, so I would
Yes.
stop.
Also, please try and make this particular note ready so that we can start practicing it and actually get what you have taught us today, so that we'll be prepared for the next class. Thank you, sir.
All right, okay, I'll do that. I'll make it available right after this class. I'll try and get the video uploaded, and once the video is uploaded, I'll make both the video and the notebook available to you as well.
Thank you, sir.
All right.
Okay, thank you, sir.
All right, you're welcome.
Thank you, sir.
Thank you very much, sir.
You're welcome. You're welcome.